This is the video lecture that corresponds to Chapter 2 of Organic Chemistry dealing with alkanes. Alkanes are the first group of hydrocarbons that we're going to study. They have a general molecular formula that shows that there are 2n plus 2 times as many hydrogens associated with the number of carbons. Alkanes are classified as saturated hydrocarbons. By that it means that there are only carbon-carbon single bonds, that it is saturated with hydrogen, having as many hydrogens as could be accommodated on that structure. We also refer to them sometimes as being aliphatic, meaning they're unconjugated. They don't have double bonds associated with them. We'll talk more about conjugation later on, but for now, just suffice it to say that alkanes are made up of carbons that are all sp3 hybridized. And some examples are listed or are shown here with ethane, and an example with ethane. To review vocabulary a little bit before we get too far into this, remember that in alkanes, as a rule, terminal groups are methyls, so those are the groups that have 3 hydrogens associated with them. Interior to that, there are methylene groups, so when I use those terms, you know what we're talking about. Also, when I talk about structural formulas, I'm referring to carbons that show the hydrogens associated with them, or the other groups could be not necessarily a hydrogen, could be a chlorine or a bromine or something of that sort. Condensed structural formulas where we've collapsed the hydrogens around the carbons to which they belong. And then in this chapter, you'll also get some practice with what are called line angle formulas. And line angle formulas for alkanes I'm not crazy about, but your book likes them a lot, and some students really like them. I just can't look at them and immediately see what they are as well as I can when I look at condensed structural and structural formulas. But suffice it to say, we'll get along with that. If you look at the bottom of this slide, you'll see an example asking you to draw the molecular formula for octane. Octane, oct is 8 carbons, and so what you see here is you should see carbon number 1, 2, 3, 4, 5, 6, 7, and 8. That's the line angle formula. I then converted it to a condensed structural formula, CH3, and then a string of 6 methylene groups with a methyl group at the end. And I further condensed the structure to show it like this. Most of the time we won't be doing that, though, when we get into biochem and are looking at really long fatty acids and molecules of that sort, we will be using those kinds of structures again. Constitutional isomers are another name for what used to be called structural isomers, where we have the same molecular formula but a different arrangement of atoms within that structure. An example here gives you 2 structures and asks if they are the same or if they're constitutional isomers. The way to do this is to, or the way to look at this is to start numbering your carbons, first of all, to see if they have the same number of carbons. If they don't have the same number of carbons, they can't be the same. So here I have, have I lost it? Let's see. Oh, sorry about that. 1, 2, 3, 4, 5, 6 carbons. And here I have 1, 2, 3, 4, 5, 6 carbons and some scratching. So they could possibly be the same. Then I start to look to see what kind of substituents are located. And here I see a 2-carbon substituent on carbon number 3 and a 1 carbon on number 4. Here I have on this one a 1 carbon on 2 and 1 on 4. So this molecule over here has substituents on 3 and 4. This one has it on 2 and 4. They must be different. They must be constitutional isomers and not identical. Another example here, I have carbon number 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Substituents on carbons number 2 and 3, substituents on 2 and 3. Even though they look different, they're the same molecule. So that's the easy way to figure out if they're the same or different. This next example asks to draw structural formulas for 3 molecules with the formula C5H12. And this is pretty similar to what you did in the last of the first chapter, only without any functional groups. So basically what I did here was I started out by taking 5 carbons and just running them in a row. I didn't fill in my hydrogens, but you of course would do that. I just put little lines to show where they would be, and recognizing that this should have an H here, I just noticed. So we've got a methyl group followed by 3 methylenes and then a methyl group. In the second one, which should be B, I guess if I were being more careful, there we go. I have 4 with a side chain, a methyl group, so 4 in a row with a methyl. And then for C, I have 3 with 2 methyls. And so I have drawn 3 different molecules. They are not the same. They are constitutional isomers, but they all have the same formula, C5H12. In order to master nomenclature of alkanes, you have to know tables 2.2 and 2.3, and I've put them here, and they're also in your textbook. What we're going to be learning is IUPAC nomenclature, which is the preferred nomenclature. IUPAC stands for the International Union of Pure and Applied Chemistry. And these are rules that have been decided on internationally so that when chemists in different countries talk to each other, they know they're talking about the same molecule. Basically, the simplest alkane nomenclature are unbranched, I guess I should say, unbranched hydrocarbons, where we simply have the prefix as the number of carbons and the suffix ane. So pentane would have 5 carbons and be an alkane. Heptane would have 7 carbons and is an alkane. And so those are the easiest ones. But it's very common to find alkanes that are branched, and so we have to start to add some rules on to what started out to be pretty simple. In the case of branched alkanes, we begin by finding the longest chain that is unbranched, and in this case that would be a chain of 3. So we're going to call this a propane. And then we're going to look for substituents and number them so we can identify what substituent is on which carbon of the molecule. So this is a pretty simple one. This is a 2-methyl propane, 2 and a dash to show that the methyl is on number 2 and propane is the root or is the parent structure. Sometimes we have situations where we have more than one substituent, and then we have to decide how we want to number the chain. And this is an example, an unnamed example. We'll name it in a minute, but here I have the longest chain is 7, and I have a substituent, turns out it's an ethyl substituent, on carbon number 3, and I have a methyl substituent on number 5. It just so happens in this case that I numbered 1, 2, 3, 4, 5, 6, 7. If I'd done it the other way, 1, 2, 3, 4, 5, 6, 7, I would have still had substituents on carbons number 3 and 5, and I'll talk about why I did it this way in just a minute. Sometimes the same substituent occurs more than one time, in which case we number the parent chain so that we have the lowest possible numbers. So in this case down here, I've got a hexane, and I've got a methyl group on carbon number 2 and carbon number 4. So I've numbered it so that I have the lowest possible numbers, 2 and 4. If I were to number the other way, I would have 3 and 5, which are bigger numbers than 2 and 4. We use the prefixes di, tri, tetra, etc. to indicate the number of repeats. So this would be a 2, 4 dash dimethylhexane. And again, tells me I have 2 methyl groups, 6 carbons as my parent chain, and they're located on carbons number 2 and 4. As we saw in a previous example, sometimes we have more than 2 different substituents. In this case, we're going to list them in alphabetical order and number to give them the lowest numbers possible. If you find you're in a situation where you can go either way with the numbers, number them in such a way that gives priority to the alphabet. So I suggested a couple minutes ago, why would I number this starting with the number 1 here instead of the number 1 over here if I was still going to have a 3-5 set of substituents? The reason I did that is because by numbering in this way, I can have ethyl, which is lower in the alphabet or closer in the alphabet to A, and I would have methyl coming second. So this would be a 3-ethyl 5-methyl heptane. When you use this nomenclature, and we're looking at alphabetical order, we don't use the di, tri, tetra, sec, tert prefixes. And so we simply go with the root name of the substituent. So this example I have here, I have a hexane, I have 3 substituents, I have methyls, a set of 2 methyls on carbon number 2 and an ethyl on carbon number 4. So this would be a 4-ethyl, because I discount, I don't pay attention to the di part of this. And this would be a 4-ethyl 2,2-dimethyl, alphabetizing by the methyl, hexane. This example asks you to write the structural formula and IUPAC name for the structure below. Again, I have a little bit of difficulty with this, but what I did was I found the longest chain that could be done. So I've got a 1 and a 2, I don't know why it's doing that, and a 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I made a mistake here. You see if you can find my mistake, and we'll go over this in class. And then there's an assignment, a short assignment. Draw the structural formula for these molecules that I have listed here below. Get started on doing some drawing and naming of structures in the problems that were assigned, and I will look forward to going over some of these with you in class. Thank you for listening.